have this nice Taylor polynomial problem in a Lagrange error bound, it's possible we could do this. All right. It's really not all that bad there. So I'll try and explain it to you, make it make sense in your head. But the first part of this, you're supposed to find a fourth degree Taylor polynomial. So it gives us all this nice information, right? F of zero, F prime of zero, and then it gives us a couple of things to find the second derivative and the third derivative. And so what I'm going to do is take that second derivative there and that third derivative there, and it says about x equals zero. So I'm going to plug in zero for that second and third derivative. So f double prime of zero tells us it's negative f of x squared. So that means it's negative f of zero squared, which is negative f of zero. F of zero, they tell us that's equal to 2. So that gets a negative 2 for the second derivative at 0. And then the third derivative is this little formula right here. So I started with that, plugged in 0 for the x's. F prime of 0, they told us that one was equal to 3. So I had 0 times 3 for that to get 0 for the third derivative. All right, now they told us the third derivative is this. The first part of part A asks us to come up with the fourth derivative. So this is a product because you're multiplying two things together that involves variables. So I'm going to use my product rule. So I did first function times it by the derivative of the second. Now when you do the derivative of the first derivative, you get the second derivative, but you have to leave the inside alone and then remember to times it by the derivative of the inside. So that's where that 2x comes from. And then I did plus the second function and then times it by the derivative of that first, which was negative 2. And then I plugged in the 0. So there's the fourth derivative. And then I know if I'm going to write the fourth degree Taylor polynomial, I need to plug in 0 for all those x's. So if I plugged in 0 for that x, that became 0, 0 for that x, that became 0. F double prime was negative f of x squared. So that was negative f of 0, and f of 0 was equal to 2. So that's just negative 2, but your times that by 0 anyway, so you get 0 for that first spot. And then f prime of 0, they told us that was equal to the 3. And so I got 3 times that negative 2 right there. So I'll get negative 6 for the fourth derivative. So if I'm supposed to write a fourth degree Taylor polynomial, I'm going to start with my main definition of what a fourth degree Taylor polynomial is. And it says about x equals 0. So I did f of 0, f prime of 0, x is the first over 1 factorial, f double prime of 0, x squared over 2 factorial, triple prime, x cubed over 3 factorial, fourth derivative, x is fourth over 4 factorial. F of 0, we know is equal to 2. F prime of 0, we know is equal to 3. So I plugged in the 2, I plugged in the 3 there. F double prime, that's what we calculated up here. That is the negative 2. And so negative 2 over 2 factorial is just 2 times 1. So I just cancel out those 2's real quick, add the negative x squared right there. F triple prime of 0, we said was 0. And so that was 0 times stuff. So that whole term went away. And then the fourth derivative, we found that to be negative 6. So I plugged in negative 6 right there. And that was x to the fourth over 4 factorial. Now, if the numbers ever get too large, you can leave that as negative 6 over 4 factorial. You're welcome to leave it like that. But I knew 4 times 3 times 2 times 1 was just 24. So negative 6 over 24 reduced to negative 1/4, x to the 4th. So there's our fourth degree Taylor polynomial there. So convince yourself, hey, you could do that. You know that main definition of a Taylor polynomial there. You could find what you need right there and just plug the items in. And we're going to rack up some points there for that part A. All right, brings us to part B, our friend Lagrange error bound. Okay, so I see Lagrange error bound, and we're using the fourth degree. So technically n is equal to 4, the fourth degree Taylor polynomial. And then it says like the absolute value of the fifth derivative is less than or equal to 15, which means the highest that fifth derivative is going to be 15. That they're telling us what the maximum of that fifth derivative is, given that we're working with the fourth degree Taylor polynomial, right? So it says use Lagrange error bound to show if this approximation is within that of the exact value. So they're talking about an error involved. So let me just remind you, you can rewatch the Lagrange error bound video notes, but this is what the Lagrange error bound is. It wouldn't hurt to just throw that formula down on that page. Spend a little time memorizing that. But the Lagrange error bound, it says the error is less than or equal to the maximum of the n plus first derivative. So if you're working with the fourth degree polynomial like we are here, it wants to know what is the maximum of the fifth derivative. And it's always absolute value bars right there. So it's just the maximum of the fifth derivative, which it kind of gave us that. It did give us that. And then x minus c, the c is the center, like that's about 0. So c is 0. N plus 1, that's to the fifth. N plus 1, that's just like a 5 factorial. So again, the n is to the fourth degree. So when I go 4 plus 1 and 4 plus 1, that makes that to the fifth power and then a 5 factorial. And I need to know what is the highest of that fifth derivative. That's really just the Lagrange error bound right there. So if we spend a little time and have that down, it's a very doable problem. So the maximum of that fifth derivative, they're told us the highest that that next derivative goes is 15. So there's my 15. And then so that was this part of it. And then it says x minus c. The c was 0, so it's just going to be x to the 4 plus 1. That's going to be x to the fifth. And then over n plus 1 factorial, it's over 5 factorial. And then on these problems, there is talking about f of 0.1. Now, you know that inside number right there, that's always like f of x. That's the x right there. So the x is 0.1. This is a no calculator problem there. So I automatically converted that to the fraction and made that 1/10. And so all I did was plug in the 0.1 or the 1/10 for the x. And then you're supposed to show that this is smaller than that 1/10 to the fifth number right there. Okay, so pretty doable. I rewrote that 5 factorial. I wrote it out. And then when I had that 5 times 3, that was 15. That canceled out that 15 on the top. And so then you have this 10 to the fifth, but then also on the bottom, you have 4 times 2, which is 8. All that stuff is on the bottom. And so this Lagrange error bound turned into this guy right here. And we're just supposed to write down that that's less than or equal to that 1/10 to the fifth. That's what they're talking about. Show it's within that 1/10 to the fifth. So we could handle doing Lagrange error bound. I know we haven't done that a lot. But that's a pretty doable problem right there if we spend a little time studying that. And then you don't even have to do this step. Like we know in the past when we did our series stuff, we know that this is true since this denominator is bigger than that denominator. You don't even have to do that step there to get your full credit for it. You got to use Lagrange error bound. I would write that formula down and then use it and then calculate it right there. And then you just have to write that down. So using Lagrange and then showing that gets us our credit for that stuff there. All right. And then regardless of how you did on the Lagrange error bound, we could all get letter C. Letter C gives us a new function, gives us a couple pieces of information, and it just says write the second degree. Because this is just the second degree Taylor polynomial. We could handle that. We just need a second derivative there. So when it gave me the first derivative, and it says about x equals 0, so I found g prime of 0. I plugged in 0 for those x's. So it was e to the 0 times f of 0. E to the 0 was 1. F of 0, they told us, was equal to 2. So I get 2 for the first derivative of g. And so I know the g of 0, I know the g prime of 0. Now I need to figure out g double prime, which means I need to take this derivative on my own. So I'm going to do the product rule right here. So I did first function times it by the derivative of the second, plus that second function times it by the derivative of the first. And then I'm supposed to plug in the 0 for all the x's there. So e to the 0 is 1, f prime of 0. They told us that was 3. So I got 1 times 3 to get 3 for that first part of it. And then I had to do f of 0, e to the 0. E to the 0 is 1. F of 0, they told us was equal to that 2. So I got 3 plus 2, which gets us a 5. And if I got a second degree Taylor polynomial for g, I'm going to start with, again, our main definition of a Taylor polynomial. So I'm going to go g of 0, g prime of 0, x to the first over 1 factorial, g double prime, x to the second over 2 factorial. We can handle doing that. And it's a really good problem. They really assess you, like, did you know that main definition of a Taylor polynomial and able to do some basic derivatives, kind of figure that stuff out there. And it's really just testing you over that because you kind of know, you almost knew most of the stuff there. You just had to find a couple remaining items there and then plug it into your main definition. So g of 0, they told us that was 4. G prime of 0, we figured out that was 2. And then g double prime, we really figured out that that was equal to the 5. So 5x squared over 2 factorial, which is just 2. And then you got that second degree Taylor polynomial. So make sure you practice this stuff on your own from scratch. Do some stuff again if you have to there. Spend a little time. We can handle getting that. That could be one of those things like we could get those points and the rest of the nation is really going to struggle with stuff like that. So do the best you can with that and let me know if you have any questions. Canoe.